Okay, all right. The volume of the room is really, really good. So hopefully you'll be able to hear us. Like I said, I think they can hear us in Galveston County. So I'd like to welcome you to the NAL First Thursday program. Today is April 2nd, and yesterday we celebrated the launch. Yay! Yeah, huge round of applause for the launch of Artemis 2. It was really exciting. So I am coming to you today from the moon, or at least that's the background picture anyway. So our speaker today is Judith Allton, who is a NAL member, as well as a recent NASA retiree. So Judy's talk today is going to focus on NASA's Genesis mission. She was involved with the Genesis Solar Wind Sample Return mission from the beginning until her retirement from NASA last year. Judy started her multi-decade career at JSC in 1974, working with the lunar samples from the Apollo missions. Her work initially involved opening and dissecting the Apollo soil drive core tubes. Say that 10 times real fast. She developed significant expertise in handling lunar materials inside a nitrogen glove box and the curation and archival of astromaterial samples. Her catalog of Apollo lunar surface geological sampling tools and containers is considered a gold standard to researchers, and it has more recently been used to help inform the Artemis planners. So go Artemis. Judy contributed substantially to the planning, design, procurement, construction, and continual cleanliness monitoring of NASA's cleanest spacecraft assembly room in order to meet the 1998 readiness for flight for the Genesis payload cleaning. Her analytical chemistry background, combined with more than 4 decades of astromaterial curation experience and interaction with planetary geochemistry community, was valuable throughout the planning and procedure development for Genesis, from pre-flight through recovery and post-flight curation phases. She was present in Utah when the space capsule returned and crashed in 2004 as part of the team that recovered the solar collectors. She served until 2025 as curator of the solar wind collectors at JSC, where samples are cleaned and shipped to scientists worldwide. Judy's expertise continues to inform the current and future generations of astromaterial scientists, curators, and archivists. So in addition to over 40 publications for which she is either the lead or a contributing author, she also was instrumental in providing educational materials which led to the production of the JSC-1 lunar soil simulant. Judy holds a BS in chemistry and an MA in geochemistry, both from UT Austin. She did, however, enter college as an art major and is quite the accomplished artist. She also is intensely interested in crafting and sharing stories which will inspire future generations of planetary explorers, as well as all of us. All right, so I'm going to go ahead and bring up Judy's presentation, I think. Try that again. This was working a minute ago. I'm not showing it at all. All right. Who jinxed it? It did, didn't it?
Yeah.
Indeed. Yeah. Well, get to see all my lovely try it this way. I think we've got it. All right.
Good afternoon, everyone. I'm glad you're here to learn about Genesis. And for you folks online, I'm pleased that you're here too. And I noticed that we have online someone who's critical to the Genesis mission, especially the recovery in Utah. And that's Karen McNamara. So I didn't know she was going to be online, but she's the one that we can ask questions of. And she can also correct me when we're done, and that would be good. We'll have a better picture of what happened.
It's great to see you, Judy.
Okay. Karen, you just sounds coming out of the walls. It's just impressive here. Thank you. All right, Genesis was the fifth discovery mission selected. That was in 1997. And the Discovery Program initiated a series of small missions that were focused and supposed to be innovative, led mostly by PIs. They had some say in the management of the mission. So this was a different approach. It started a little before Dan Golden, but faster, better, cheaper, it fit right in that part of the program. The missions were organized and proposed by the principal investigator, usually an academic scientist, and he'd recruit the science team, write the proposal. Those that were, they even partnered with, say, professional mission managers. Genesis, for instance, the PI was Don Burnett from Caltech, and his first manager was Chet Sasaki at JPL. And they worked closely together. I think this is remarkable, looking back at some other examples that happened after Genesis. They worked hand in hand, met once a week for breakfast at Pine Burger in Pasadena to cover all the details. Genesis did two things I thought were remarkable. Part of that were included in the budget and should have been for a lot of other missions. They funded two analytical facilities on the ground to analyze the samples after return. These were complex facilities. One was a megasims at UCLA, and the other was a resonance ionization mass spectrometer at Argonne. And the other thing, budget-wise, was to have funding in there for the curation of the samples after return. So it was an end-to-end, we're going to get the science out of this funding. The mission was originally in the first proposal entitled Sus Uri, which is the name for two distinguished cosmochemists at the time. But on second round, the Genesis was still competing. The name was changed to Genesis, and it was selected. What was the big picture they were trying to answer? Back in the mid-20th century, there was this simple model notion that the sun and the planets were formed from gas and dust that came together, accumulated, and eventually ended up as the sun with the leftover planets with the planets left over from the gas and dust. So there was an assumption that this was somewhat homogeneous. Consequently, a lot of the information used to determine what that original composition was came from meteorites. The thinking being that some of the first material solidified would capture what the initial composition was. Now we know our planets are different, but if we had a real good idea of what the initial starting material was, we'd have a better chance at unraveling the individual planetary histories. So Don Burnett, through this proposal, was suggesting that we should sample the sun directly rather than take information from old rocks. And I think that's about all introduction I had to say. This picture, which was taken by the Driller team, is one of my favorites. This particular one is the 2017 solar eclipse. And he and his associates take lots of these pictures, but you can see it has just a whole lot of detail. You cover up the sun, and what you see streaming off the sun in this picture is solar wind. And that's what the Genesis mission proposed to capture. And capture it we did. This is one example. The set across the top are from SOHO instrument, a large spectrometric coronagraph, and it's got timestamps on it. And in October of 2023, there was a series of coronal mass ejections that were quite strong. Toward the end of the month, they were known as the Halloween storms. And this particular one is what's shown in these pictures. It's taken from a video. It was a strong enough storm that a lot of the solar observing spacecraft were knocked offline into safe mode. But Genesis had this plate of collectors hanging out there, and they caught the coronal mass ejection ions. Subsequently, it was analysis was done by a Japanese team who measured the solar wind speeds from the coronal mass ejection at 2,000 kilometers a second, which was the fastest at that time. So in general, we capture solar wind, we return it to Earth where we can look at it in very sophisticated laboratories. We curate it and make it available for scientists worldwide. So you get a lot of people with clever ideas and good instruments and having samples available for them to analyze. When you do this, when you arrive at a number for what the composition is, other people can verify it or dispute it. You can approach the problem using different materials because we had a lot of different materials that were flown on Genesis. So sample return is a good way to recover from disasters and a good way to get a lot of answers that you wouldn't get if it were a remote spacecraft. This is a cartoon showing a solar wind leaving the sun. And the picture here is 5 of us holding one of those arrays of hexagons that were collectors for the solar wind. These were very pure. They were highly polished. They were like mirrors. We kept them pretty clean. As you can see, We handle them wearing these suits. There are HEPA filters on those belts. So, and the intake for breathing is around the mask. So anything you exhaled went out the back through a HEPA filter. That was part of it. You can see 3 dark hexagons in this picture. That's diamond-like carbon coated onto silicon. And Karen McNamara, who's online, knows a lot about the diamond coatings that we use as collectors. Okay, what, when, and where? Where is Earth Sun L1 and some of the other solar observing spacecraft like SOHO and ACE are also hanging out at Earth Sun L1. So they give us a comparison for what the spacecraft were recording that the solar wind was consisted of, that you could compare with something that is in a laboratory sample. They were exposed, Genesis samples were exposed to the solar wind from December 2001 to March 2004. We collected mostly bulk solar wind, but we were also capable of collecting solar wind when it was in high-speed regime, or when it was in low-speed regime, or coronal mass ejections separately. This gives the solar physics people some information to work with for how the solar wind is formed. Let's see. The hexagons fall in the category of passive collectors. There's a list of the different materials: silicon, sapphire, aluminum, gold, diamond-like carbon. And then there was a concentrator. This was to concentrate the solar wind received so that we could make better measurements, especially for oxygen and nitrogen isotopes. And the concentrator had silicon carbide, it had CVD diamond. Karen knows a lot about this, and the diamond-like carbon. So there were 3 different materials on which the solar wind was concentrated, giving more options for analysis. Then why we do this to get the high precision that's required for planetary science and to allow those multiple techniques that we talked about and sample at different regimes. If you take one of those silicon hexagons, look at it on side, that's what we're looking at here. This is just the top 100 microns of it, but it's a cartoon to show you the solar wind being a yellow arrow. As it impinges on these shiny mirror surfaces, we'll get embedded subsurface, and the scale bar on that's 100 nanometers. So this cartoon shows a collection of solar wind atoms at 50, 60 nanometers below the surface. This picture was taken at the Jet Propulsion Lab on the 10th anniversary. This is their engineering model, and it's configured as it would be if it had been on station collecting solar wind. So you can see the spread, and the 2 people in there are for scale, right? The hexagons were on these different arrays, is what we called them. 2 of them are pointed out with the blue arrow, stayed exposed to the solar wind the entire time. Then the 3 that were in that stack that rotates in and out, those were for the different solar wind regimes. And this one, the pink arrow, shows one that be extended to collect low-speed solar wind. The green one, coronal mass ejection, and the red one, high-speed solar wind. The golden arrow points to the concentrator. And here's a close-up of that. This is during assembly. This was designed mostly at Los Alamos and put together there. You can see there's a broad, about 15-inch diameter opening that the solar wind would come into, and it's an electrostatic mirror. So it's reflected from the surface back to the focal point that you see in the middle. And that quadrant, that's with the 2 dark quadrants and the 2 light colored ones, faces down. So that's where the incoming solar wind was focused into this smaller area. That's about 2 inches. So you could get about a 20-fold increase in the solar wind, which gives you enough to get some signal above background. This is the composition of those hexagons is shown in this color cartoon. You can see most of them are gray, either light or dark. So you can see that the preponderance of the hexagons were silicon. Preparing the payload, we cleaned the payload with ultra pure water. Now this is water that's been cleaned up to have a resistivity a little greater than 18 megaohms, which means that the ionic concentration of everything that wasn't water molecules or atoms was in the low parts per trillion. It's like hungry water, and it just is really pretty reactive. It's pretty clean. A lot of other solvents and cleaning agents have things that leave residues behind, which is why we wanted to use this. JSC curation produces this water. It takes up a whole room for some of the components. Others today include a 5,000-gallon tank and many hundred feet of PVDF Teflon kind of tubing. What you do is you keep this loop continually flowing, and you pump pretty clean ionized water through it, and you use ion exchangers to take out inorganic stuff. You use UV to kill bugs. You use a different UV 185 to break up organic molecules. You use filters to take out particles, and you can get it this clean if it keeps going. So you have to hook on this loop to use the water. You can't put it in a jug. You can't expose it to the air because it grabs stuff out of the air. So in this picture, we're cleaning a piece of gold foil, which was intended to collect nitrogen, in a vat of ultra pure water. And yes, it's exposed to air here, so there's a little bit of a contamination source there. It's not totally isolated. The other smaller picture inset is a device through which we pump this ultra pure water, and it adds megasonic energy to it. It's like an ultrasonic in a handheld, and you can move it around. And we use that to clean the larger items like the science canister. The JPL folks brought the payload to JSC. By remembering right, whether it was, we did a practice run on the engineering model. They showed up in the summer, and we wondered what these folks from JPL would be like, you know, Hawaiian shirts, Bermuda shorts, all that kind of stuff. And I figured they probably thought we were going to have baseball caps and overalls. I don't know. It was a meeting of cultures, and it turned out to be really fun and really good because everybody was really dedicated to what they're working on. I think you guys have probably experienced that. Anyway, the 3 folks in this picture are from the JPL engineering staff that did the design work and the fabrication. They brought their flight hardware to JSC, took it apart, gave it to us to wash, then they're putting it back together. This is the final closing of the science canister. You see the arrays are all folded up. The lid's going to close. You can identify it by the white paint pattern on top. And I remember when we closed this, and we had worked so hard. And I have to say, you can't appreciate it from the pictures. These polished hexagons are just gorgeous. And you can say you've seen yourself in a golden mirror or a diamond mirror. It was so beautiful. It closed up, and I wondered at the time what it would look like when we opened it again. Because we closed it up here at JSC, and it wasn't open until it got on station to collect the solar wind. Okay, went from JSC to Lockheed Martin in Denver, and it was integrated into the sample return capsule. When they finished putting all their parts together and making the craft flyable, it went to the Cape for launch, and it was launched on pad 17A at Cape Canaveral on a Delta II. I like that picture, but I guess my favorite part is the size of the guys in the yellow raincoat at the bottom. I think pad 17A and B no longer exist, but that was pretty neat. Okay, we're off to collect solar wind. And why? Oh, this is a configuration for collecting the solar wind, same thing you saw in that other picture. But this gives you the amount of solar wind collection time on the different collector surfaces. The bulk solar wind, 853 days, and the regime solar wind, ones that switch in and out, they had to share the time for that. So it's a little bit less, a little over 300 for high speed, low speed, and a little less than 200 for the coronal mass ejections. There was another collection device in the SRC lid, which you see, which was molybdenum-coated platinum foils, and that was for a PI experiment. He was going to do some radioactive counting after they were trying to assess what the radioactive species were in there and the amount of them in the solar wind. So that's what it was. So while I was collecting, we were back home practicing for sample return. And you might think, well, those really beautiful hexagons look pretty fragile. Well, they were. And it was decided that they wanted to catch the incoming sample return capsule in midair so it would not hit the ground. I'm getting into Karen's area expertise here, so write your questions down for her. This was so cool. This is a picture of one of the helicopters that was out there to catch the incoming parachute. These guys practiced, and this picture I put in here to show you, they've taken the doors off, and in the back seat, you see a winch. They've done that so they can lean out, see what they're doing to make the catch and to run the winch. And underneath is a long rod, and you can see the barbed hook at the end. That's for catching the parachute. Somewhat like this. And this is a practice session. I believe these guys had about 40 practice runs and never ever missed. And the ones that I did see were like a ballet in the sky. They were just absolutely beautiful and choreographed. Now I'll share a little bit of a story I tried to write up to tell younger people how this part of the mission was supposed to work. The incoming sample return capsule was supposed to deploy a drogue chute. This purpose was to pull out this rectangular parafoil. And the helicopters, two of them, the primary and a backup, were hanging out about 10,000 feet. And they would listen to the call out from Hill Air Force Base for the altitude and the vector, getting ready, to dash, to be on station to catch it. And they could catch it. On the practice runs, they did it, and it was gorgeous. When the parafoil came out, it would put the return capsule in a big, lazy spiral. And so the helicopter crew could sneak up on it from the back and using their hook and hook it just left to the center point. That was the plan. And it was gorgeous. And there was not a doubt in my mind that they would have done this. Okay, so the practices went well. This is return day, September 8th, I think. Let's see. Karen is in there. She's a redhead with a purple shirt on the left side of the picture. And this bunch of the Lockheed crew is going to be the recovery people. And well, that's it. You can see we're ready. We got all of us, our heads going through this checklist of all the things we're going to do when it goes right? Okay. And here we are, sitting there at the UTTR, watching and listening to reentry. So we can hear the call outs from Hill Air Force Base, as can the helicopter pilots, but we can also see a picture of a tumbling SRC. And that's not looking too good. And when the next pictures come in after it has crashed, forgot what I was going to say here. It'll come back to me. Oh, the pilots didn't have visual. All they hear are the numbers. They knew the numbers were dropping too fast. And something like impact. They said, repeat that. Okay. Oh, this part Karen will like. She did this. I don't want to go back. I'll mess up the system. No, that's all right. Just picture they're back there looking at that. As soon as we saw how we're sitting here, knowing it's not good, and then we get the pictures that show that it has crashed. We all kind of look over to the left. It's a bunch of cabinets. And in those cabinets were the things that we had put together, principally Karen put together. She was up there well ahead of all of us. She made all the arrangements in Utah for stuff that went on there and interfaced with the UTTR people. And what was in those cabinets was shard collection kits. These were put in those big orange buckets from Home Depot. There was cameras, scale bars, tweezers, gloves, lots of pre-numbered vials and bags. I think we had several thousand of them up there. Okay, off. We got the stuff to go get it. We're ready to go get it. And we sit and wait. And I really want to know what Karen has to say about this. It took a while for management that was further up the scale to say, yeah, you can go out there. Okay, this you can see, it's kind of augured in, as Amy said, to about halfway, but you can recognize the sample return capsule and it's not in good shape, right? The helicopter in the background is an Army heavy lift helicopter. They gave us all kinds of good help out there. On the other hand, you can see it's not a huge crater. That's not a terribly big hole. It was damp and the mud was soft. Next thing we had to do was sample for toxic gases. There was some worry. I've forgotten what the source was. I think it had to do with batteries. Karen may remember that because she helped the mishap investigation for a lot. So she might be able to answer your question, Mario. Ask her if she's still on.
Sorry, what was the question?
Let's wait for the questions.
Okay.
We'll wait till you're done.
Okay. All right, this is a field. I'm surprised I didn't capture one with Karen in it because she's in it in most of these. But you can see the science canister is one broken open. It's bent. There are things coming out of it, and the sample return capsule is damaged pretty well. But there's one of the bags with the barcodes with the retrieved sample in it in that other picture. The decision was made by these folks out there. Karen, and she may have talked with Eileen by phone, I don't know. They decided that the top of the canister was in better shape than the bottom, so they rolled it over onto a tarp just to kind of keep it all together and had some help wrapping it over that, and it came back on that heavy lift helicopter to this clean room, which had been set up there in the hangar at UTTR. In this, we had expected to have their normal return set down by the helicopter outside, have it rolled in, kind of saw open some latches, extract the canister, put it on a nitrogen purge, and pack it in a special box for shipping back to Houston. That's what all this was set up for. But Karen and the folks working out in the field delivered, and the help from the Army people, delivered it to this clean room before nightfall on that same day that it happened. It was very hot out there. The Army brought them meals ready to eat and some other stuff. I was in this clean room, just looking at the other end of it. When they brought it in, this is them rolling it in the door. The picture in my mind was, this is an emergency room, and that's a gurney, and they're bringing in a very injured patient. And these are the doctors surrounding the patient, trying to decide what needed to be done next. Most of these people in this picture were the engineers that did the design work on it. And after looking things over, they had a plan. And one of the things that was done at this point in time, someone with a mirror on a stick stuck it in the canister, and they thought they saw that the target was still intact. So that was a big plus. And they got the plan. Can't remember what's next. Okay, I was going to say, the biggest thing that made this go smoothly in my mind at that time was credit cards, cell phones, and FedEx. And I say that because they had figured out a plan for disassembling that canister. So the JPL guys went into Salt Lake City to the Home Depot store. I went into Salt Lake City to the Sam's Club and the restaurant supply. I bought more stainless steel tables. I bought lots of polycarbonate trays. I even dropped by the art shop to buy some really fine brushes, but don't tell Karen because I don't think I was supposed to use them. Anyway, credit cards allowed everybody on the scene to go get the stuff they needed right away. Cell phones were key because we could call back to JSC, and of course, everybody here was willing to do anything to help. I think the same situation applied at JPL for stuff that they needed to take the canister apart. Now, cell phones, let me back up a second. We could call here at JSC and say, we need this, this, and this tomorrow. And the person on the phone here would get it, and FedEx would show up the very next day. I was impressed FedEx could show up out there because it's kind of remote. Also, the cell phones in 2004 were not as handy, or maybe they were handier in my opinion, than they are today. They were the kind that folded up and they had push buttons on them. Anyway, cell phone service was not well developed, and that was very remote. So in order to use your cell phone, you had to go to the parking lot and get in line of sight of Deseret Peak to get your service. So a lot of this important business was conducted in the parking lot outside the hangar there. Okay, close up of the disassembly, and you can see the big red shears, which was a Home Depot purchase item. It's Don Burnett in the far left. So he was on the scene and a very hands-on type, useful person. Another scene of trying to take collectors off those arrays. These are face down. Now, most of the things on these arrays popped off during the crash. And what you can't see, especially because it's under that thing at the bottom, there's people laying on the floor, taking pieces off like broken under the car. And what they're doing, they're removing the pieces that were still attached because we knew the location on the batch number for all the things had they still been attached. The concentrator. It wasn't quite as round when it returned as when it left. And we had a rehearsal here to survey how straight it was so they could do the calculations for the focus. Well, there was no point in doing that on something like this. So that task went away. But you can see that the concentrator target holder, that 2-inch disc with what you see are 3 whole quadrants and a partial fourth one, they were recovered pretty much intact. And the missing pieces in that fourth one, about 90% of that was recovered. As you see in the picture at the bottom is a picture taken later. So that's a good news. This one shows some of the whole pieces that were recovered. The gold foil that was intended to collect nitrogen from the solar wind nitrogen, and the polished aluminum, which I think was for noble gases. That round piece is a bulk metallic glass, about 3 inches across. It was kind of a late add-on addition. You know how when you get a PI that wants to put something else on there that'll collect more solar wind, that's kind of the mindset. And I was given that to clean, and I told him it was very fragile. I was so afraid to wash it even, and I was very careful. And lo and behold, the most fragile piece is intact right there. And the science done on this was made the cover of Science in 2009, and it had to do with trying to explain some energetic particles that had been measured in solar wind done for Apollo pieces. But the bulk of the work was picking up pieces from those. There was about 300 of those hexagons altogether. These are the pieces. An intact hexagon was about 10 centimeters point to point, but you saw the scale size in there. So these barcodes and some of these containers were some of the stuff we sent ahead, and some of the stuff that people sent later. You know, we had other things to put them in, but you can see how that was documented. Okay. Re-entry was September 8th. All this stuff was back at JSC on October 4th. Over 12,000 pieces were documented. That's Don Burnett, the PI, doing his part up there, and 2 of the people helping to count all that stuff. The other advantage, when we needed expert helpers, you could call and say, send people that know how to pick this stuff up and document it. So these people came from curation here. No training needed. They just get off the plane, they come work, they knew what they were doing. And the guy on the left, his name is Jack Warren, is the one who opened the very first Apollo rock box from Apollo 11 in a vacuum glove box. Okay, back to the lab. All of these things that we brought back had to be cataloged, and which would be an inventory, characterize what they were, and publish a catalog so that scientists could figure out what sample would meet their research needs. And we had some instruments in there. We had a very good optical microscope. We had an ellipsometer, which is seen in the middle picture, and that was Karen's area of expertise and FTIR. So she had a lot to do with acquiring the instrumentation that went in this lab. The catalog that was produced, and we had about 2,800 samples characterized, I think about 10 or 15 years ago, would provide an image. It would tell the user what material it was in, and it would say what regime of the solar wind they were looking at. Most people started measuring what was in bulk solar wind because it was a lot more of it. The regimes were scarce. Whoops. Okay, for cleaning the samples, that ultra-pure water we clean the hardware with, we used it to clean samples as well. And this is a device adapted from the semiconductor industry at the time. You put a tiny sample on there of the vacuum chuck, you close the lid, and the megasonic energy came through, and it would spin at 3,000 RPM. So that's a good way to shower blast your piece and take the particles off. For an allocation, I'm going to just use one example, and it's part of the target. Silicon carbide target, it went into a special mount. That mount has a standard mounted nearby, and that's common practice if you're using beam instruments to make measurements. So that was packaged in a special mount and sent to UCLA for oxygen isotope measurements. Here's a picture of their megasims, which was part of that funding expenditure. And this is not a room full of individual instruments. All of these parts are connected together. The sample is put in at the far end of the room. It's accelerated and curved, with magnets and stuff. So it was pretty slick, and they got data. This is the piece they analyzed, and I'm going to share this. This is that inch radius thing, and you can see there's a colored radiation. The pink part is the part that has more solar wind, and the blue on the circular radius is less. So there's a set of analytical points across here that the oxygen measurements were made from. There's a set of neon points which help calibrate the focus across these, and a set done for nitrogen. The 2011 volume of Science featured the target and the oxygen and the nitrogen results. Okay, how is Genesis science possible? This is taken from a paper by Amy Ravage. So it's possible because the ions were returned to Earth. We had 6 ways of collecting it and multiple collector materials. So they all reacted differently to the crash and the cleaning and the measurements. And so it just opened up a lot of options. This is the prioritized list of measurement objectives that went in with the initial proposal. Those that are successful are in bold. First one is oxygen isotopes, done. Nitrogen isotopes, done. Noble gas elements and isotopes, and even in the regimes. A lot of the number 8 elements are in minerals that people trace the content for to sort of figure out the histories of planetary stuff and meteorites. Carbon is missing. There are samples that might still be done on, if any of you are interested. That list was objectives that were proposed. You got the samples back, and there's now other ways other fields could use them. The samples interact with planetary materials because you can use them maybe to make better gauges on space weathering. We have known doses of radiation in these samples. That was careful. So if you want to look at structural alteration or morphization, it could be used for that. The solar wind formation modeling includes how do the ions get lifted off of the sun? Does it have to do with their ionization time or their ionization potential? And Genesis samples can't address that. So other people can use it. I go back to Amy's graphic here. She's using a picture to say you can investigate the whole cosmos by looking at what's in these samples up close. So that's it. Legacy for science, that's how many samples we allocated, how many individuals participated, 42 institutions, 11 international, and the samples are still here for new generation, new questions, using better instruments. a legacy for sample curation. The ISO 4 particle clean sample handling laboratory was established, and applying the UPW cleaning to flight hardware and Genesis samples. And now some pictures. Don Burnett, Eileen Stansberry, and Amy Aravich is still working in this stuff. And this last picture was taken in 2024. These are the remaining people in JSC curation who had worked on Genesis. And 3 of those people are gone, but the youngsters that are left are well trained. Thank you.
Can you go back one bit?
Go back one.
Thanks. Okay, thank you.
That was awesome. Don't go away. Don't go away. All right, we're going to start off by taking some questions in the room. So anybody, Mario, did you have your hand up? Did you have some questions? No?
Not at this point.
All right, yes.
So I'm a little bit familiar with the Parker probe, which I don't believe returned anything or never intended to. But it occurs to me that there may be something that you learned from your return samples that benefited the Parker program that was later launched.
Okay, so the question in the room has to do with the partner probe. Parker, thank you.
Eugene Parker.
Parker probe, and whether there was anything that that Judy and friends learned from the Genesis sample return that then benefited the Parker, right? Close enough?
Yeah, yes.
Okay. English is my second language, so.
I was privileged to see the Parker lunch. I went with our EPL people. Sue knows about that. I'm thinking, Genesis came back first, and we were really deeply buried in trying to analyze these samples. A lot of time was spent trying to clean them. I think our major contribution about a better estimate for what's in the solar wind for using for planetary science purposes, it's still coming around. A lot of people still use the meteorite stuff, but we are interacting with heliophysicists who are using Genesis data. The heliophysicists started with trying to analyze the solar photosphere for lots of elements. You can't do all the elements in the photosphere, and the error bars are generally a lot larger than you can get on the sample in hand, but they have been using Genesis data to, especially, I'm trying to remember what elements. There's a break point. They're kind of thinking about when does stuff condense and where does it differ from, say, land-based estimates. And there's an over or under abundance of volatiles compared to, so it's that kind of relationship. As to what did we learn from Parker, which I thought you were going to say that would apply to Genesis. I'll just say there's not been a lot of crosstalk between heliophysicists and people that understand the data from Genesis, except for people modeling solar wind formation and for Graves and the estimates for the photosphere balances. Does that help?
Yeah, it's interesting.
Okay. Other questions in the room? Aria.
Hi. At the beginning, you said you wanted to sample the solar wind directly rather than the leftover stuff, all of us, planets, meteorites, and figure out the constituents to the makeup of the solar system from that. And if I'm understanding correctly, the list that you had with some bold-faced and some not bold-faced, was that the derived, let me rephrase that. Was that list what you were expecting? Thank you, Lisa, appreciate it. Was that list what you were expecting and what you did accomplish in terms of the boldface? And the others are not, like the number 5, carbon isotopes. You didn't find any of that, or was destroyed in the crash, or for the 19 on the list here.
Okay.
Any chance you could summarize the question for people online?
Oh, summarize the question. Mario's looking at the prioritized measurement objectives and asking, the bold ones were accomplished, but the ones that weren't done remain to be done. I'm not sure I can rephrase your question. What I will
I'm asking, you were hoping to find the constituents of the makeup of the solar system from your sampling directly of the solar wind. And you didn't know the answer when you started. That's why we did it. So in the end, and I know you had problems, of course, as you elucidated with the, problems on reentry. Was this the list that you found? Was this the list you expected? And then is the boldface what you verified, and then what's not boldface was left because you don't know, because the samples were contaminated or destroyed or whatever?
Okay, this list was the list of objectives submitted with the initial proposal. This said, here's what we'd like to measure. And it's a combination of things that would help answer the question of leftover gas and dust, modified a bit by what might be possible. And some of this stuff is not as relevant to deciphering the starting materials for the rocky planets as other stuff. So that's the mixture, but the bolding came afterwards. That's what we were able to measure now. Like number 14, fluorine abundance, that was desired. And we tried to get at it by measuring bromine abundance and stuff like that. But those people were measuring something like 400 atoms. It was very hard. So that's what this is, that mixture.
Okay. So the boldface is what you actually accomplished and verified from your anticipated list. The rest was left to chance and not achievable.
Yeah.
Okay.
Question.
Related to that last statement he just made about not, so the ones that are not boldface, is it still up in the air whether they exist or not? They exist, but they got muddled up because of the landing, or we weren't sure if it was something in the first place. Is it like a combination of that and we just don't know at this point?
Okay, if it's on the list, it's
It would be
probably
expected.
it's probably there or it's useful.
Okay.
And it's separated a bit by feasibility. But the task was not to identify stuff, but to measure how much was there. And if it had different isotopes, what the relative kinds of isotopes were. For instance, magnesium is very popular. There's 3 isotopes of magnesium. And people that study rocks and stuff tend to think that that's been kind of constant. There's not been an outside factor that fractionates them. So they want to look at the relationship among isotopes. I probably should have gone into oxygen more. Oxygen has 3 isotopes, 16, 17, and 18, which you know. And they've got a ratio among those 3, generally 16 to 18, that identifies the Earth, identifies the moon. They're similar, so they say, common ancestor or some relationship. The difference among those 3 isotope ratios makes Martian rocks a little bit different than that, and asteroid rocks a little different than that. So that oxygen isotopic ratio is a little bit like using DNA to see who's related to who. So it's that kind of thing, and that's why that floated to the top, and that they made a special instrument to try and go after the oxygen numbers.
Okay. Well, this is not going to be easy. Actually, I think what I'm going to do Yes, great, thanks. So I'm going to go ahead and get our presentation.
You have another
I
question?
have one more question.
Okay, hang on to your question. Let's get out. Okay, we're going to take one more question in the room. Go ahead.
Yeah, what do you see as the status of the Genesis samples now? And is there someone on site that actually works or is the curator? And then is there an effort to encourage like the Caltechs and the JPLs to use the sample or to check those out to do more work on them?
Okay, current status of the Genesis Curation Lab at JSC is that processing on those samples has been paused, that they will try to fulfill any requests that came in before a certain deadline. The intention, at least my understanding, was just to cut back on the resources used to run that lab and help use those people elsewhere. But they're not going to throw them out in the trash. It'd be more an order of mothballing it. I don't know how that's going to go. Is there a current Genesis curator? Her name is Dr. Alyssa Madera. She's a deputy branch chief for curation. And she's recently appointed, let me say that, okay? What was your other question about? Oh, other academic people that worked to Genesis team, because Don Burnett was just the kind of guy that called family, and we kept having virtual meetings every year, even during the pandemic, because we all knew each other. Don Burnett could cajole people into doing work. So he got a lot of extra work, but I think there's no funding to support that, and that's really the big problem. Don is older than I am, and I think we may be getting tired, and we're left with a lot of unfinished work sitting around.
All right, thank you. All right, we have some comments that I want to get to. See if I can, oh, come on. This was working earlier. It really was. All right, so we have some real expertise online. So Dave. Okay, so terrific presentation. This is Dave Lucky. He developed the Genesis Bus Flight software that managed two of the onboard science sensors, the JIM and the GEM. Also developed the bus flight software for managing concentrator voltages to collect samples. Okay, so he worked with Don Burnett and several other scientists from Los Alamos, and was published as one of the contributing authors. So my guess is that you would know him. And then we've got a little bit of a chat conversation between Karen. And yes, he worked with Roger Wade. So there's a little bit of, we've got some other expertise online. Karen, your name has been mentioned a number of times, or is there anything you would like to add at this point?
No, I think Judy did an amazing job at covering a lot of material, and it's a long story, and she really captured the essence of everything. I think the one thing I would point out is the whole discussion on that list of objectives. The 19 objectives were kind of a wish list. The actual official objectives of the mission was a shorter subset, the top ones that you saw. carbon being the one that was really difficult, and that's because of contamination. But the ones that are lower down on the list were things that were more, we wish we could do this, but it's going to be really, really hard. So that's the only thing I would add. It was fantastic, Judy. Great job.
Okay, thank you. And just so you know, the volume control in the room does not work.
So I was told that there's a Zoom interface control for the volume for remote speakers.
There's actually no.
That's not the Zoom interface.
No, it's not. It's actually in the facility manager's office. I verified it. So, okay. Any other questions for Judy? We don't want to talk about Zoom all day long. So, any other questions for Judy before we let her go?
I'd like to have one comment, and nice to meet you, Dave Lucky. I've never met you face to face that I know of, but based on what you just said about the programming, he would be the guy that helped the onboard instruments decide which of those arrays to deploy for high speed, low speed, or coronal mass ejection. So that's neat.
Great. Great. Any other questions? All right. Okay. All right. That is going to do it for us for today. Thank you all for joining us today. Thank you all for hanging in there. We still continue to have Zoom issues, but they're getting more and more survivable some way or somehow. I just want to remind everybody our next first Thursday is going to be, I believe it is on May 7th. Does that sound right? May 7th is a Thursday. Okay, but the night before our next first Thursday, we are having another NAL social. It'll be a dinner and a social. We'll be sending some information about that fairly shortly. You'll be able to register for it, purchase your tickets for dinner. We'd like to see everybody there. It's going to be a very, very interesting program. Our speaker is a gentleman by the name of Dr. David Alexander. He's from Rice. He's the head of the Rice Space Studies Institute, and he's also just recently been awarded a couple of grants to further extend the reach of this Space Sciences Institute. So I think he's going to have a lot of really interesting things to say. So watch your inboxes, and we'll get that information out to you shortly. And again, I'd like to really give our thanks to Judy for the excellent presentation and, talking about a part of JSC that a lot of us don't really know about. So thank you very much.